Hello, welcome to Stat 134, Lecture 26. Last time we talked about the CDF, which is the probability that x is less than or equal to x. So for example, if our random variable is the exponential lambda and c is some positive constant, then the CDF of the exponential is drawn below, and the area from 0 to c, the green area in the density, that is 1 minus e to the minus lambda c. So that would be the value of the CDF at c. If you have a mixed distribution, this takes values between 0 and c. It can't be larger than c. So all of the mass that from the exponential that isn't between 0 and c would need to be concentrated right at c. So that's why at c we have a single mass of height e to the minus lambda c. And so the CDF is as shown. So now today what we're going to do is we're going to review student responses from the from the concept test from last time. We'll review the MGF and we'll see how to use the CDF to find the expectation of x. So last time we did this concept test. Suppose you're trying to discreetly leave a party. Your time to leave is uniform from 0 to 2 minutes. However, if your walk to the exit takes more than 1 minute, you run into a friend at the door and must spend the full 2 minutes to leave. Let t represent the time it takes you to leave. So the CDF does not look like this, as one person writes. However, it is for the wrong reason. The probability shouldn't jump to 1 at 1, because it should jump to 1 at 2, because if a person doesn't leave in the first minute, then they leave at 2 minutes. So a person correctly says that here, and I've drawn for you both the CDF and the density. So this should make sense. I gave you guys some practice with another mixed distribution. So here, stoplights at an intersection alternately show green for 1 minute and red for 1 minute. So a car arrives at the light at a time distributed uniformly between 0 and 2 minutes. In other words, if they arrive in the first minute, they get a green light. If they arrive between the first and the second minute, they get a red light. Now, x is the delay of the car at the lights. Graph the density in the CDF. So clearly, x only takes non-zero values between 0 and 1, right? So the probability that the person arrives at a green light is a half, and the probability that they arrive at a red light is a half. If they arrive at a green light, then x is 0. There's no delay. So this is going to be a mixed distribution with a mass of a half at 0, and then the remaining half probability will be distributed uniformly between 0 and 1. And so the CDF will then look as shown. Let's just review MGFs quickly. So if x is a random variable and t is a real number, then the MGF, moment generating function, is the expectation of e to the tx. And so if x is gamma r lambda, so it has the given density function with variable part as shown, then the moment generating function we showed last week is lambda over lambda minus t to the rth power for t less than lambda. As another example, if x is uniform 0, 1, so its density is 1 for x in 0, 1, I had you guys calculate the moment generating function. So that is the integral from 0 to 1 of e to the tx times 1 dx. And so that's 1 over t e to the t minus 1. Now, an important property of the MGF is that if two moment generating functions are equal in a neighborhood for t in a neighborhood of 0, then the two random variables x and y are equal in distribution. So, for example, if x is uniform and y is 1 minus uniform, which is uniform, to see that y is uniform, just use the change of variable rule with g of x is 1 minus x, and you'll see that the density is 1 for y and 0, 1. So x and y, they're not equal, but they're equal in distribution. And the moment generating function is exactly the same, as you can see right here. So the point is that knowing the distribution uniquely specifies the MGF, and knowing the MGF uniquely specifies the distribution. To drive this point home, we did a concept test here where I gave you a density here, and if you're familiar with the gamma density, or the variable part of the gamma density, you will recognize that that r is 2 and lambda is 1. So and knowing that the MGF of gamma r lambda is lambda over lambda minus t to the rth power for t less than lambda, the answer is B. Furthermore, if we're given the density and if we're given the MGF and we recognize this to be a special case of the MGF of a gamma, then we can uniquely recognize that x is gamma, r is 1/2, lambda is 1. So then we looked at using the CDF to find the expectation of x for x, a positive random variable. And this is described in your book in a problem number 9 on page 324. So first we'll talk about the inverse distribution. So if you have a CDF of a random variable x, so let's say x is positive, so basically you can throw darts between on the y-axis between 0 and 1. So that gives you an IID uniform 0, 1, and you'll get then IID random variables on the x-axis. Now, the distribution x doesn't need to be continuous. For example, it could be mixed, in which case you may have a bunch of your points all going to the same value of x, as here I show if you throw darts in the yellow region on the y, then you'll always get C. So interestingly, if we're throwing darts uniformly between 0 and 1, then we get an IID of x, the distribution x. In other words, F inverse u is x. And the proof of this I write out clearly at the end of this lecture. But how is this useful to us finding the expectation of x? Well, it's sometimes much easier to calculate the expectation of x using the CDF, because essentially it allows you to avoid doing an integration by parts. So expectation of x is F inverse u, and so F inverse u is a function of u. So to find the expectation of a function of u takes non-zero values between 0 and 1. So I'm going to integrate from 0 to 1. I have my function F inverse u, and then I write the density of u, which is 1, between 0 and 1. And so this is just basically integrating the function f inverse u between 0 and 1, which is the green shaded area here. Now, to find this area, let's just reflect along the diagonal. So you can interpret the expectation of x is the area between 1 and f of x. So theorem, let x be a positive random variable with CDF f, and it can be continuous, discrete, or mixed. The expectation of x is the integral from 0 to infinity of 1 minus f of x dx. So let's see an example. So if t is exponential lambda, we know the CDF, it's 1 minus e to the minus lambda t. So to calculate the expectation of t, we integrate the CDF, 1 minus the CDF from 0 to infinity, and the 1's cancel, so you're just integrating e to the minus lambda t, and it just turns out to be 1 over lambda, as you know it is. And that was such an easy calculation, much easier than what we had done before to derive this. As another application, just for this problem, to find the expected time it takes to leave the party, you would just find the area. So we know what the CDF looks like, so we just find the area between 1 and the CDF. And so you can just see that area is 5 over 4. Okay, so that is it. Oh, maybe I should quickly take a look at this appendix here. So to prove that x, if x is f inverse u, that this is a random variable with CDF f, you can just follow basically all the steps. I'll just go down to the second to last step here. The probability that u is less than or equal to f of x. So because u is uniform, we know that the probability that u is less than or equal to little u is u, right? Because the CDF for uniform is just the diagonal line. So the probability that u is less than or equal to f of x is f of x. So this shows that the CDF of x is f of x. Okay, have a great day. I'll see you next time.